So we'll start a new topic from today, that is MOS junction. But before that, we would like to understand metal semiconductor junction itself. So let us understand this concept contact potential first. So in PN junction, you have seen that there exists a built-in potential VBI, and N side is positive because there is dopant donor dopant charge, positive charge, and P side Na minus is there, so negative charge. So positive to negative, there is a potential difference, that is VBI, and we call it built-in potential or barrier potential, or sometimes even contact potential. So why is this word contact used in contact potential? So we'll try to understand that. So normally contact means we say metal, when you put a metal on a semiconductor, that's like you are contacting a semiconductor. So then why are we having contact potential even for PN junction? So if you take this PN junction and have this built-in field like this, and if you connect a metal wire connecting P and N regions, so if you expect any current flow, then it cannot happen, because where is the power coming from then? Okay, so PN junction is just a passive component, so it cannot generate power. So it means it cannot supply current. So then what is this potential? Then how can Kirchhoff's law is satisfied? So there is no current that can flow outside, okay, even though there is a built-in potential. So you cannot read the value of built-in potential using a voltmeter. This you have studied in PN junction topic, and just kind of revising. So why voltmeter cannot read is, voltmeter, if you see how it functions on detecting small current. Voltmeter will have a very high impedance, so very small current flows through voltmeter, and that current is converted into voltage. So that's how voltmeter works. So if you connect a voltmeter somewhere here, hoping to detect the built-in potential, you won't, because there is no current flow. Then how can Kirchhoff's law is satisfied in this loop? If you see, metal wire means after all, it has some thickness, and it will actually make a contact with this P region like this here as shown, and with the N region as shown to the right. Okay, so like P and N, the Fermi levels on both sides are different, and in equilibrium the Fermi levels align. As a result, we have some charge transfer from one side to another side, because adjustment of Fermi level is going to happen only because of charge transfer. So there is a built-in potential. Similarly, the Fermi level in metal and Fermi level in P, they may not be aligning at the same level before connecting, but after you connect in equilibrium, they should align. So there must be some charge transfer, and there must be some potential drop. So similarly, between N and metal on the right hand side, and if those are like V1 and V2 in the same direction like this as shown, then if you see that V1 plus VBI plus V2 is 0. Okay, so this is how it will be there. Kirchhoff's law is satisfied. So V1 and V2 are also called contact potential, because after all, you are contacting the P region with a metal, and the potential difference at equilibrium is contact potential. The same is the case with the N region. So when we drew earlier in case of PN junction like this, with a battery like this VA, and we said that the drop across the junction in the depletion region is now VBI minus VA. So that is, entire VA is dropping across the depletion region, is what we said in analyzing PN junction. So this is only an assumption, it means now. Why? Because what we said is, we not only assumed the drops in the quasi-neutral P and N regions to be negligible, but also assumed that VA doesn't drop across left side MP junction and right side NM junction. So this is again was not explicit in the discussion of PN junction, that there can be small drop between this MP and NM when there is a bias. So you put a battery like this, and it is not that the applied voltage VA entirely appears across this junction. It can appear partly across this junction, partly in the quasi-neutral P region, partly in the quasi-neutral N region, and across the depletion region partly, and partly across this N-type semiconductor and metal. So it can happen, part of VA can drop across all these regions. But when we drew picture like this, our assumption is that VA has entirely dropped across the built-in the depletion region of P and N junction. So not only that quasi-neutral P and N regions have almost negligible drop, but also it is assumed that the left side and right side metal semiconductor contacts also have negligible drop, negligible contribution from VA. Not that potential drop is negligible. Remember that there exists V1 and V2. So it is not like we have neglected the drop across MP. No, when we apply battery, the component of VA that drops across MP is what we are neglecting. We are not neglecting V1 and V2. Remember that. Okay. So it's not like we are neglecting VBI. So let's understand the contacts a little more. So there exist two types of contacts, Schottky contact and ohmic contact. And if instead of a metal, instead of a PN junction, if you take a simple N-type semiconductor like this and apply battery, even for that we will have two contacts like this, metal and metal contacts like this. So earlier we have seen that this applied battery N-type semiconductor, this simply acts like a resistor, because this applied battery causes some field to be arising in the N-type semiconductor, and there is carrier transport, and that is due to drift, and that is like N-type semiconductor acting like a resistor, we said. But now that actually that is true only if these two metal contacts are ideal. Okay, so what it means is we have assumed the contacts to be ideal in the sense that they offer no resistance to current flow in either direction. But that's not true always. Okay, but that's not true always, because contacts can be non-ideal also. So here there's no drop across these contacts, and they allow current to pass in both directions, this way as well as this way, without distinguishing the direction of flow. Then they are like kind of ideal. Okay, then what is the meaning of ideal contact or something? So here, for that, let us study a single contact again, like this left side contact here. The metal is there, N-type semiconductor is there. Then we applied a battery. Again here, I have removed the other metal junction, metal semi N-type junction, because we are assuming it to be ideal. So what is happening here, we are not seeing. So we are studying the properties of this left side metal N-type junction. That's what it means. So if you apply a battery, and depending on the nature of the contact, you can have two types of curves. So one is something like this. One kind of characteristics, IV characteristics, is like this, and you see sometimes other kind of characteristics like this ohmic contact. Okay, so if you see this, these are the kind of IV characteristics that are possible with a non-ideal contact. But if it is ohmic contact like this, ohmic is because I versus V is linear like this. So this is like a resistor, right? How you draw. So if you just apply V and across N, you just see the curve between I and V, then it is linear, which means, and if the resistance is entirely given by N-type semiconductor, then this contact is like ideal contact or called ohmic contact. So that is also not complete understanding from the real making of ohmic contact, but for now you take it granted that this is the definition of ohmic contact. So there is no kind of resistance offered by the contact. So there is other type of contact, which is the Schottky contact shown by this blue curve, which is almost similar to the PN junction characteristics, right? So there is some cutoff region like this, and cutoff means cutoff voltage or cut-in voltage. So it is not directly starting at x equal to 0, but I is starting to rise exponentially after some voltage. So that is cut-in voltage. Then it rises exponentially. Okay, Then if it is exponentially, then sometime definitely it will match with ohmic contact, you might, and cross even ohmic contact. No, that is not possible. So this is the ohmic ohmic IV characteristics are coming because of resistance offered by n-type semiconductor. So this curve can only go and merge with this, but can never exceed this red line curve. Okay. And on the left hand side, you see that zero current for a very large voltage, and a breakdown happens here. So it is almost similar to a PN junction diode. So such MS junction, such metal semiconductor junction or contact is called Schottky contact or Schottky junction. And a diode made of such junction is called Schottky diode. So this, like PN junction junction diode is used in many applications. Like for example, you have a bridge rectifier, which you might have studied for full wave rectification. So similarly, we have Schottky diodes employed for various device applications. Okay, in various electronic circuits. So let us study first how a metal semiconductor junction looks. So let us look at the equilibrium band picture of a metal semiconductor junction, and then see how these rectifying characteristics can come. Let us see this picture, metal, and then there is this n-type semiconductor, and the band diagram is shown this way. When they are separate, they are not joined together. And metal, it is shown with two energy levels and one quantity called Q phi m. So one is Fermi level, another level is E naught. Okay, and the difference between these two levels is Q times phi m. And if you see what it is, Q phi m is called work function of the metal. Basically, phi m has units of potential. It means because there is Q. So Q phi m is work function of the metal. Why is it called work function of the metal? Why? Because I'll just tell it over here. So earlier we have seen that Fermi level is like is the top surface of liquid, contained in a vessel. Okay. So these are like electrons, and Fermi level is like the top surface at 0 Kelvin. And if the temperature is raised, then it is like having an agitation in this liquid. So liquid part of liquid goes up, comes down, and some other places it comes down. So the average level will be at Fermi level. So this kind of picture we have seen. So work function is like if you try to take some water droplet out of this semiconductor, out of this vessel, so it will be on average, it will be around EF. It is not like you will take water drop or take water first out of some level like this. No, water is up to here. It is slightly going above and below depending on the agitation. So if you want to take water, a small bit of water out, you will be taking on average from this level. So similarly, in metal also, if electrons are slightly jumping and coming down around the level EF, and if you want to take an electron out of the metal into vacuum outside, that is what is called work function. And so the energy will be the vacuum energy level minus the Fermi energy level. So that is what we see here. So E naught minus EF, this gives you work function. Similarly is the concept on the right hand side, semiconductor. Even though there is no energy level at EF, even though there are no electrons just around around EF, because there are no energy levels around EF or even at EF, if you actually try to take electron out of the semiconductor, it can either come from electrons in the conduction band, or they can actually be electrons from valency band also. Okay. So on average, you see that electron, if you see from statistics, you actually pull out so many electrons out of the semiconductor. And if you see on average, the energy of those electrons, if you want to see, it will be like energy as if the average energy of all those electrons is EF. So similar concept is extended to semiconductor also. So it is kind of an average energy, not exactly like definitely you will be able to take an electron from the Fermi level into the vacuum. No, because there are no energy levels at EF in semiconductor. So it is an average energy of electrons when you take them out of semiconductor. So that is why we have similar concept of work function that is defined especially for metals. we borrow the concept of work function for semiconductor also and denote it as Q phi S. S subscript is for semiconductor, M subscript is for metal. There is another important concept in this band diagram, that is this particular quantity, which is the difference between E naught and EC. So this is called electron affinity. Okay, so why is it called electron affinity? So in atomic physics, if you see, there is an atom, so with positive nucleus and electron cloud surrounding the atom. And if it has high electron affinity, it means that it has the tendency to attract electrons. If you add an electron to the neutral atom, it will become ionized and it releases some energy. Okay, so that the energy that is released actually is given by electron affinity. This is for a single atom. But in semiconductor, that is in solid state physics, so what is electron affinity is that, say you add an electron in atom, you add an electron means that electron will start revolving and it becomes an ionized atom, right? So but in semiconductor here, when you add an electron, you add an electron in the crystal with zero velocity. So it is like you add it at EC. Okay, so you added an electron at EC because you are adding an electron into the crystal with zero velocity. So it is means the potential energy, kinetic energy of the electron is zero, and it is inside crystal, so it has only potential energy. It means the electron energy is EC. So the energy required for that is what is defined as electron affinity in case of solid state devices. So E naught minus EC gives you this electron affinity, which is denoted by Q chi S for semiconductor. So you know that E naught, both E naughts will be same. Okay, even though they are far apart, E naught is vacuum level just outside the metal or outside the semiconductor, so they will be zero. Okay, so E naught, these E naught levels will be aligning each other. So this is how you draw a band picture first for two distinct materials before joining them together. Okay, you draw individually the band pictures on the left hand side for material 1, on the right hand side for material 2, with all the important energy levels marked. So here semiconductor, right, we have E naught, EC, EF, and intrinsic Fermi level, and EV. Now that we join metal and semiconductor, and let us see how things change. How will the band diagram look in equilibrium? So this is the metal and semiconductor we have, and in equilibrium we have seen, we have done problems also in tutorial. In the equilibrium, so first thing is that Fermi level will be constant. It doesn't change with position. So draw a constant Fermi level. This is how you should draw band diagram for materials of different type, which is called a heterojunction. Okay, so drawing band diagram for a heterojunction. Hetero means not of the same material. So first you draw EF constant, then draw E naught above EF over metal side and semiconductor side, then join E naught smoothly in the junction region. So you know that charge transfer occurs between metal and semiconductor. Yeah, before coming to that, let me just tell one more concept here. So if you ask metal or n-type semiconductor, which is more like P and which is more like N, in the sense, if you want to understand this metal semiconductor junction also in terms of already familiar junction and that physics, then we have to try to see with the PN junction, because that is the junction that we have been familiar with till now. So metal semiconductor junction, so we want to understand in terms of PN junction. Okay, so can I say that here, since it is already N, so metal I will consider as P simply? Can I say that just like that? It is not possible. Just as it is, you cannot say that. But you might argue, why not? Because metal has more number of electrons. So electrons are much high in number in metal than semiconductor, even if it is n-type semiconductor, we can only have 10 power 17 or so per centimeter cube. But in metal, we can have up to 10 power 21, 10 power 22 electrons per centimeter cube. So definitely metal will be like n-type. If you say that, that is a wrong conclusion. Why? Because if you want to analyze using the already learned p-n junction concept, then you have to see which actually supplies electrons, which actually supplies holes. That is what we have to see. So, okay, here there is no, the hole concentration in the n-type semiconductor is very less. So there we don't need to talk about hole concentration or hole movement. So let us focus on electrons itself. So since metal has more number of electrons and n-type semiconductor has less number of electrons, that is concentration, can we say that electrons flow from metal to n-type semiconductor? No, we cannot say that the net flux of electrons will be from metal to semiconductor just because concentration is high on metal side. Why? Because actually you have to see, what you have to see actually is the Fermi level position. If you see that metal Fermi level is much lower than the semiconductor Fermi level. So at any given energy, say E dash or E1, whatever, E dash, at that energy, when you join them at that particular energy level, that is when movement happens between metal and semiconductor. You will see that the occupation is more in n-type semiconductor than in metal, because the metal Fermi level is much below. So the occupation in metal at E dash is much smaller than the occupation in the n-type semiconductor. So even though concentration of electrons is less in n-type semiconductor, so its concentration at a given energy level is still more. So electrons will move from n-type semiconductor to metal because Fermi level on n side is more. So electron flux is decided by the Fermi level position, okay, not on the concentration. So clearly here electrons will flow from n-type semiconductor to metal. So metal can be seen as P and n-type semiconductor as N. So in terms of junction, it is a p-n junction, similar to a p-n junction. So so there is a charge transfer because Fermi levels were not aligning in the equilibrium, before joining them. So now you have E0 here, you draw. So there I will leave some portion for charge transfer and anything. So I will draw little energy levels as if as they are seen before forming the junction, quite far away from the junction. So here I will draw a little far. So E0 is somewhere here we draw. This is where we saw E0. And this is EF and this is EC. And EV, EI, EF can be simply drawn like this. So this is how E0 can be drawn, or the bands on both sides can be drawn. And now what you have to do is you have to join E0 smoothly. Why you have to join E0 smoothly? You know that E0 is like the potential just outside the device. If there is any discontinuity in E0, which means there is a infinite electric field, which is not possible because the slope of the potential gives you electric field. So there cannot be a jump. You cannot have E0 doing like this. There cannot be any jump like this. Why? Because this jump indicates that the derivative of E0, which is potential just outside the semiconductor, is infinite. Okay, so which means high infinite electric field, not possible. So we have to join things smoothly. So since metal has high concentration of ions, even if electrons are lost or electrons come here into the metal, so the potential drop in the metal can be assumed to be 0, like how we draw a P plus N junction. So I will just make this flat almost, because I assume that any change in potential happens in metal region for a very small distance. Over small distance changes will happen, not like in semiconductor. So I'll connect like this. So this is material quantity. So Q times chi S. So material parameter does not change whether as long as you are in the same semiconductor, material quantity, which is electron affinity, should not change. So EC also just follows E naught. So with the same difference chi S all over. Okay, so don't change EC position with respect to E naught. It is a material dependent fixed quantity, like energy gap of the semiconductor. So now EV also, just we said, and like energy gap of semiconductor, it is EC minus EV should be maintained constant, because that is a material dependent parameter. So like this. Now EI also can be drawn like this. So this is how we draw band diagram for a metal semiconductor junction of this sort. Now clearly, if you see what is happening here is that if you draw rho as a function of x, you see that it is n-type doped, and EC minus EF, the difference is increasing towards the junction. So there is a depletion here. So if you see that there will be positive charge in the semiconductor like this, and corresponding negative charge will be there in the metal, and that metal negative charge, you see that E naught minus EF, this difference has come down. So there is high negative charge. So it is like, because metal can have, concentration of electrons. Here the concentration is coming because of ionized dopants, which has a fixed concentration of Nd. But here electrons, they can just they can just come into metal region and then vary rapidly. So if you see, both areas will be same areas under the two curves on both the right hand side and left hand side. So this is how the space charge density looks. And you know that electric field direction is given by slope of EC. So electric field is in this direction. So this is the direction of electric field. I am not drawing the curves. And you see that electron drift is in this direction. Okay. And diffusion is in what direction? So diffusion is towards left, because electron concentration has decreased as it is coming towards metal region. Okay, so electron diffusion is like this. So both are balancing each other in the depletion region. So this is called depletion region. So in semiconductor, so in metal semiconductor junction also, you will see in this type of junction, there is a depletion region in which there is an electric field, and inside depletion region, electron drift and electron diffusion balance each other under equilibrium. Okay, so it is like half picture of a PN diode, PN junction, just that the P region is replaced with a metal. Okay, so this is what the picture we have. Now if you see what happens and why it gives rectifying characteristics is as follows. So I told you this metal semiconductor junction. Okay, now let me complete this, because I might ask you to draw p-type a metal semiconductor junction. When the semiconductor is p-type, I might ask you as assignment or something, so know how to draw this. So after you draw E naught on both sides and join smoothly, finish. Now basically maintain, draw EC. Okay, just a second. This one is third point. Why is it third? Because second point is you have to identify, you have to leave some gap, because we have left initially this much gap we left for junction region. Leave some gap around the junction to connect energy levels in the end, towards the end. So leave some gap, like for example, depletion region, etc. Leave some gap around the junction to connect energy levels towards the end. So now in the remaining region, draw E0 above EF over metal side and then join E0 smoothly in the junction region. Now fourth point is draw EC, EI, EF, sorry, EV below EA0, maintaining same Q chi S for E0 minus EC all over. Okay, so that's how that completes. That's how you draw. Now if you see what happens when we apply positive charge, right, positive voltage. So we have seen that this kind of metal semiconductor junction has a potential difference. So when you integrate this, when you from this row, you will get electric field in this direction. So there is a built-in potential. So in what direction the built-in potential is? So this direction there is plus, because electric field is coming from positive charge. So this is positive charge, this is negative charge. So there will be some built-in potential like this VBI. Okay. So where the semiconductor is positive and the metal side is negative. So if you take this as the reference, that is semiconductor as the positive terminal and the metal as the negative terminal, negative side for built-in potential calculation, you will see that the built-in potential is nothing but this. So this is the built-in potential VBI. Okay, and what is this value that we have to see? So this value is simply how much the EF has moved down. That much this E0 has moved down. So EF, how much it moves down can be seen from this difference, because EFs should merge. So this is the difference between EFs. That much EF comes down, and to the same extent E0 comes down, and variation of E0 is nothing but variation of potential, and that is the built-in potential. So what is the difference here? It is Q phi m and minus Q phi s. So this is simply Q times phi m minus phi s, which is denoted as, and Q times phi m minus phi s is denoted as Q times phi ms. So phi ms is phi m minus phi s, and we have seen that the semiconductor is, and here it is phi m is greater than 0 in this case. So Q phi ms, because phi m is greater than phi s, is greater than 0 in this case. All right. So and VBI is positive towards the semiconductor, negative towards the metal side. So if any semiconductor, any metal semiconductor junction you take, if you mark semiconductor as plus and metal as minus, then if there is a built-in potential, and that built-in potential you can simply write as phi ms. So phi ms you write as the contact potential of a metal semiconductor junction. Always remember the units, because contact potential means you, for a PN junction, you know that contact potential is given by VT ln Na and d by Na square. Fine. but which side is positive, which side is negative. There you remember that n side will have donor charges, so n side should be positive because that is positive charge. P side negative ions will have, so negative charge, so negative potential. So there you clearly know that VBI value is VT ln Na ND by Ni square, but the direction you know. So n side is positive and P side is negative. So similarly, in a metal semiconductor junction, if you put plus on the semiconductor side, negative on the metal side. So you remember this. So you should put positive on semiconductor side, negative on metal side, and that potential difference can be seen as phi ms. So this is the picture you have for metal semiconductor junction. Now what happens if we apply bias? So if you apply bias, and I told you this kind of metal semiconductor junction, metal is more like P here. So we have seen that because n-type Fermi level is at a higher position than the metal side Fermi level. So this is actually forward bias. Why? Because metal side is connected positive. So it all depends on which is more like P and which is more like N. So if metal side Fermi level is more, then metal side will act as negative terminal N side. Okay, so it all depends on the positions of Fermi level. So here this is kind of forward bias. In forward bias, what happens is that so metal side Fermi level slightly rises up. So metal side Fermi level slightly rises up. Why? Because you are decreasing the energies, slightly goes down. Why? Because positive potential, if you apply towards metal, their energies go down little bit. So EF comes down, E naught comes down little bit. So if you bring E naught to a lower level, so the difference between E naught on both sides will be less. So there will be lesser potential difference, or in other words, lesser field. So you will have diffusion dominating over drift because you have reduced the drift component. So there is a built-in field EBI like this, electric field built-in potential like this, and that is balancing the diffusion current from N to P, okay, or M to N, whatever. Now that you have applied some potential, it actually falls across the depletion region in N region, reducing the built-in field. Okay, so now E built-in minus EA. Okay, so that is a reduced drift field. So drift actually becomes less than diffusion. So you see that electrons actually are diffusing from n-type to metal because electron Fermi level position is higher. So electron diffusion current is this way, Jn diffusion. All right, fine. So clearly forward bias, Jn diffusion is there and depletion region is there. So you will have a positive current flowing like this entirely due to diffusion of electrons in the depletion region, and in the quasi-neutral region it will be drift because small field will be there in the quasi-neutral region. So this is how it is. So it is more like PN diode theory where drift is suppressed when you apply forward bias and diffusion remains the same. So diffusion is more than drift, and it is all diffusion current in PN junction forward bias. Now what happens in reverse bias? Why is it behaving like a rectifier or rectifier characteristics? Why does it have? So metal type, N type. So so you have N side. So this is VR reverse bias. Let me call it VF maybe. So you have VR reverse bias. N side is connected positive terminal. So what happens is N side energy levels go down. So already E naught is here. Okay, so EC is here. So if EF is here. So if these levels are pulled down, okay, so this can only happen. This increases the depletion region. Okay, so this increases the depletion region. So it is like increasing the resistance. So it's like how we saw in PN junction, if the depletion region is widening, then the current actually will not increase. It will be decreasing. It will be slowly increasing. That is what is the reverse saturation current. Okay, so I hope you understand. So this is this much discussion is sufficient. Let us move on to MOS junction. So basically, you have a Schottky junction, in which we have seen forward bias. It can conduct just as in PN junction diode, and in the reverse bias, same thing that happens with PN junction happens with this Schottky diode also. So the Fermi level has to come down on the right hand side, N side. So that will come. So these will come down only by increasing the depletion region like this. So which means it will increase the resistance. So that's how we'll try to end this discussion here. And one thing about ohmic contact. So we have not discussed about metal P-type Schottky diode, so that you can do it as homework. So draw band diagram for a metal P-type Schottky junction. So this is homework. You can find this in textbook also, but try it first and then look in the textbook. One word about ohmic contact I just want to add. Ohmic contact is something not easily done. Just like you put say something about ohmic contact. So you see that the band diagram is something like this, right? So EF is here. For a Schottky contact, it is like this. So EC is like this. So I'll just draw. So this is EF. So this is EC. So I'm just drawing how EF EC look. That's all. Because this is N-type semiconductor. I'm not drawing all. Okay. So now forward bias means what? I said this will go down a little bit. So earlier this is EF. So this side will go down a little bit. In other words, if I keep this side constant, this side will rise up. So my EC will go up like this, and EF will come like this. Okay. So still, if I'm finding materials which have EF somewhere in the middle of the band gap. So what I mean to say is, if see here EF is somewhat close to EI. So if you see that all materials are almost all metals have their Fermi level somewhere lying between the energy gap. Okay, some metals have Fermi level aligned very close to EV. Sorry, I mean very close to EV. Metal Fermi level will be there, and some metals have their EF very close to EC. Okay, so it is not like you will have a metal whose Fermi level is well inside conduction band or well inside valence band. I mean, you know, very rare to find, or almost I don't think there is any metal like that. So it is all material properties. So why it is not there, we cannot say. It is not there in nature. So that's how it is EF and EF of the semiconductor and metal are. And now what happens is, you see that there will be electron diffusion this way. Okay, electron diffusion this way, electron diffusion. Okay, so and electron drift is this way, which is small because the field is negative. So it is going, electrons are going this way. So this is what it is, and the difference is what is giving rise to small exponential current. I mean current that exponentially increases with voltage. Okay, but there is another mechanism where current can flow, not only just this electron diffusion and drift, which balance each other. That is the problem we have, because this diffusion only can, this electron drift can only be suppressed and only diffusion current can dominate, that happens only for applied voltage close to cut-in voltage. So either you should be very close to cut-in voltage or increase the voltage beyond the cut-in voltage. Only then this electron drift will almost suppress and only electron diffusion will be there, and you will see it increasing with voltage exponentially. But so, which means that if only these two mechanisms are there, I will always find characteristics almost zero current, because diffusion has not become strong enough and drift is still there. Only when drift becomes very small, because applied bias cancels the built-in field which happens at cut-in voltage, that is when it starts rising very significantly, because drift almost has died, only diffusion is seen. Say, that's how you can see it like. So so there is another kind of mechanism instead of these two, and I want that to dominate, and so that current will increase like this. So I cannot depend only on these two, say. So I need to have another mechanism where current flows, and then it just flows just like this, increases with voltage right at center. So for that, what is done is, the other kind of mechanism we know for current transport is tunneling. So for that, what they do is, so if this is metal, if this is n-type semiconductor, so what they do is dope very heavily. Instead of joining just M, instead of just joining, making just depositing metal on n-type semiconductor, you convert that n-type semiconductor surface to n plus. Okay, so you can convert the n-type semiconductor to n plus, and on top of n plus you put metal. Okay, and n plus to n, because both are electrons, n plus supplies electrons this way, or you can actually current can flow this way. So it is n plus and n. So the flow between n plus and n will not have any problem at all, because they're all electrons. So there won't be any difference between n plus and n. So electron movement can easily happen between n plus and n. So we have to see what is the kind of movement between m and n plus. So if the doping is very large, then what can happen is, so now let us say m and n plus region, how the band diagram looks. So the band diagram looks like this. So this is metal side EF, and this is EF here. This is where EC starts, and then doping is very high, so it has to fall very rapidly. It will fall. So this is EC. The difference is also smaller. EC minus EF is smaller, and it falls very rapidly because the slope of EC gives you field, and dE by dx, you know that it is n q n d by epsilon s. So if nd is large, slope is large. Okay, so slope of electric field is large, so the variation of EC also should be very rapid. All right, so when this is so rapid, this thickness is so small that electrons can tunnel this way. Okay, so from metal, so they tunnel this way actually, because you in forward bias, right? So you have to draw this in forward bias. Now this way, and Fermi level has gone up, and EC is rapidly varying. So now that EF has become more, and here some electron states are there. Say if you consider this energy level, some E dash, so you can clearly see that electron occupation on this side is more, because EF is above than the EF on the metal side. So occupation is more on this side than on the metal side. So electrons can actually tunnel and come like this. So this is electron tunneling, even though there is a physical barrier. So this is electron tunneling. All right. So because ideally electron cannot exist, because that this variation is EC, means below EC there is forbidden gap. but still electron is going. So that is why it is called tunneling. Okay, so classically this is a barrier, but electron is able to move past the barrier. So that is why it is called tunneling. So this tunneling is happening from right to left. So the current electron current will be from left to right. So that is conventional P to N type, P to N conduction in the forward bias. In the reverse bias also, this field only will increase, thus increasing the tunneling current. So even in the reverse bias, the Fermi level will go down further like this because you have applied reverse bias. So this is EF, EC. So this is EF on metal side. And that time, this is electron tunneling will happen here in this direction. And that current also will be very large. Okay, so this also current will be very large. So this is forward bias. So reverse bias. So this is equilibrium. So you see that in forward bias also there is electron tunneling. In reverse bias also there is electron tunneling, which will only increase actually. So overall, if you see the characteristics, you can actually get this kind of characteristics. So this is ohmic. So ohmic contact means it's not like you put a metal on N-type semiconductor, but you make an N plus region, N plus, you make it N plus on top of N region, and then you just contact with M, and you will have an ohmic behavior, because there is no problem in electrons traveling from N plus to N or N to N plus. So here this junction, N plus N junction, we have assumed it to be kind of ideal because there is no hindrance for electron flow. Both are N type. Okay. So with this ohmic contact discussion is finished. So we have finished the Schottky contact, why it is kind of rectifying properties. It is having rectifying properties, and how can we make an ohmic contact, and what is the physics behind ohmic contact. So next thing is metal oxide semiconductor junction, which is a crucial junction, which is the concept that we normally discuss before introducing field effect transistor, which is what is the widely used transistor in the world now, not only now, for many decades. So this is the next topic is metal oxide semiconductor. So in short, it is MOS, metal oxide semiconductor junction. So let us just try to go through it and go through the salient points of this. As I tell you, this is what we have to discuss before discussing the device called MOSFET. Okay. So MOSFET means metal oxide semiconductor field effect transistor. Why is it called field effect transistor? We will see later, but yeah, we can see it now, and then give motivation to study MOS junction first. Okay, so what is field effect transistor? Actually, before bipolar junction transistor, field effect transistor was proposed. So let us say you have okay, horizontal or vertical, I'll write. It's okay, no problem. You have a metal, you have a semiconductor, you apply a battery, and there is a current flow because they say N type, or let us say P type now. So you apply a battery and there is a current flow. Okay. So what you want is, even if you apply, there should not be any current. So the current should be controlled based on some third, in the sense power supply will be there mechanically. What power supply will, this is what is mechanical switch. You know, it's not like you have not applied so this is some RL, so this is some load resistance, there is a switch. it's not like power is not there, before you switch on. So it is there, just that the potential drop is actually occurring across the switch. All right. So when you connect the switch, okay, then current flows. So like that, I have a load and I want an electronic switch. So this is basically a mechanical switch. I just use my finger and press the switch. So this is mechanical switch. So instead of mechanically controlling a switch, I want an electronic switch. In the sense, I want to control it with some voltage. So I should have some voltage here. Okay, I should apply some voltage, say plus, with reference to say the same minus sign. And it should, depending on if it is positive or negative, it should close, and it should conduct, and if it is negative or zero, it should not conduct, whatever. So plus minus are not significant. The concept is that I should have a voltage that actually controls this on and off. Okay, so now if you just see, if you try to say come up with this electronic switch, how do we come up with this electronic switch which actually switches on and switches off, or conducts and doesn't conduct, depending on a third terminal voltage? So here you have two terminals, one terminal here, one terminal here. So these are the two terminals of the device, and there is a third terminal here which actually controls whether current can flow in these two terminals or not. So this is the simple semiconductor, p-type semiconductor, and if you connect a battery like this, there is a current flow. So there is a current flow like this, but I want to control this current, put it zero, or allow the current to pass based on a third third terminal. So the idea that was proposed is, say if I say I ground this, so this also, so instead what I'll do is I'll do like this. So this also I'll just put ground. So what I'll do is I connect this side to ground, and then I put a metal field or a plate like this, okay, separated by some distance. So this is basically insulator. So there is a gap in between, and I'll apply some voltage here. So what I do is, if I apply positive charge to this plate, this positive charge comes here and negative charge should come here, right? So what it means is, the positive field like this repel these holes, so it will push the holes into this ground. And if I make sure that this actually entirely gets depleted, okay, this entire p carriers are depleted, and it will send the carriers to ground, and equivalently there is a positive charge on top. It is as if these holes come and travel like this and then go to the top plate, so giving rise to positive charge on top and negative charge, negative acceptor charge in the p-type region. So there are no movable carriers in the region anymore. All that is there is impurity ionization, ionized impurities, but there are no mobile carriers. When you don't have mobile carriers, how can there can be any current? Because current conduction happens only when there are mobile carriers. Otherwise, you can have current conduction in vacuum also, but in vacuum there are no carriers. So that is why, unless you put carriers, vacuum also doesn't conduct. So how do you put in carriers in vacuum? That is what is this thermionic emission and olden days vacuum tube devices. You just somehow emit carriers into vacuum, then I will control the flow of electrons in the vacuum by using third electrode or whatever. So that is how those vacuum tube devices work. So because carriers cannot be found in vacuum, they had to release carriers into vacuum first, and then they control the movement of carriers. So similarly here, when carriers are not there, you cannot have any current flow. Okay, so that is why it is off. If only you put 0 here, so you can have a conduction. So simply you can have conduction. So it is like you put a positive charge to deplete this and you switch off, and for negative voltage or even 0 voltage, this can conduct, because for 0 voltage, there is no charge on the plate on top and in the P region. So this is the transistor that was proposed in 1920s, and it took almost 40 years to realize this transistor. In 1960, this MOSFET was first successfully was made, even though it was proposed, I think, in 1926 or 27. That was the year this concept of this field effect transistor. Why is this called field effect? Because you are actually depleting this charge by applying field like this, by getting, so this is what is the field effect. So that is why field effect transistor, because you have changed it. I will not get into the definition of transistor, why something will call the transistor. That is basically transfer resistor. That is combination of, transistor is basically transfer resistor. Together it is called transistor. Okay, so you are transferring resistance. That is the kind of thing. So let me not get into that now. So this is the field effect transistor that was proposed, and it was made in 1960. So this is so if you see, there is this electrode, okay, and there is this insulator, and there is the semiconductor. Okay, so this insulator, when they made MOSFET, it was oxide. It was silicon here, and it was oxide here, and it was metal on top. So silicon or semiconductor. So it became a metal oxide semiconductor field effect transistor. So that's, so before studying the MOSFET, so you should first study this junction. Okay, so what kind of biases we should have so that this P region entirely gets depleted, or because all that is required, because unless you study this particular cross section, that is this metal electrode on top, insulator and p-type region, you cannot study what flows when you put a battery on either ends. Okay, so that is the reason to study MOS junction. So so we have seen that it is MOS junction is what we have to study, and this, if you see, it is a capacitor, because after all there is an electrode on top, and this whole P region is acting like an electrode. It's a thick electrode, you can say. This is a very thin metal electrode, and whole P region is providing the negative charge. All right, when it is forward, when it is positive bias on the metal and negative bias on the P side. So whole P region has become negative. So it is a thick electrode of that sort, but it is still an electrode of capacitor. It is like that because there is an insulator in between, and either ends we have two electrodes. So that is why it is sometimes called as MOS cap. All right. So instead of MOS junction, we sometimes refer to as MOS cap, because this field effect is simply a capacitor effect. So that is why we call it MOS cap, because it is MOS capacitor. MOS capacitor, because that is capacitor action, field action or capacitor action. So let us just see, before just 5 minutes, we will finish how this device is made, and just MOS cap, and then we will see in the next lecture. So MOS cap, how is this made? You have a metal oxide semiconductor, right? So you take a semiconductor, say p-type semiconductor. This is a semiconductor wafer. It is of so and so thickness, and you actually pump oxygen, and then at a very high temperature. So say if this is silicon p-type semiconductor, this oxygen will interact with the surface, and then it produces oxide layer. So part of it will be consumed, and then partly it will grow. So this is called oxide growth. So you will grow a thin oxide, you will grow a very purity, with high purity you grow. So this is nothing but SiO2, which is an insulator. So you pump oxygen into a chamber where silicon wafer is there at very high temperatures. So it will react with silicon, substrate, and then it will form a layer on top. So depending on how long you flow, I mean you pump in oxygen, depending on the temperature, this thickness actually is decided. So this thickness ranges from a few, normally that is employed in devices, this thickness. A few nanometer to tens of nanometer only olden days, but now it's all like few nanometers. It depends on technology node also. And then on top of this, you put, you just deposit a metal. So this is how, so this is metal. You just deposit a metal on top of silicon dioxide, and this you will get MOSFET, MOS capacitor. So how you make MOSFET, field effect transistor, we will, that is not part of this course, how to make a MOSFET, how to fabricate a MOSFET structure, and what is the process of making a field effect transistor. That's not the part of syllabus. That comes under another course actually, fabrication, VLSI fabrication. But this is some rough idea. All right, we'll stop here. We will meet in the next class.